Can you see the screen? Okay.
Yes, sir, you can.
Okay, today we will have a bit of review of what we did, and please ask questions on anything we discussed until now. Okay. So this is what we did this semester, and this is also what will be in the exam. So we started with logic, sets, relations, functions, operations, algebraic structures, posets, and then we also had graphs and recurrences. So graph and recurrences we will not do today. It is quite recent. We had also a lot of exercises, but I want to go through the first part. I also put the slides in the in Moodle. Okay. So we discussed why we need logic, and let's remember what is a proposition. It is a declarative sentence, that a sentence that declares some fact, and be both. Okay. So usually we use letters, P, Q, R, for propositional variables, and then they have a truth value of true or false. The variables. So it's either a true statement or a false statement. And then we moved on with having operators, right? Logical operators. For example, the negation, which says that the negation of a proposition P is a proposition, it is not the case that P. So, and it has the opposite value of whatever the truth value of P was. I will not go through the examples, but we should see the truth table. So it is this: P was true, then not P is false, and if P was false, then not P is true. Then we have the conjunction, which is the logical operator and if the conjunction of two propositions P and Q is that P and Q. So this means that if both are true, then it is true, and in every other case, it is false. Is it clear? I mean, we'll remember this, I hope. And then we have disjunction, where this is the logical operator or. So for P and Q being two propositions, P or Q means that at least one of them is true. So maybe both are true, then the disjunction is true. But also if one of the two is true, then P or Q is also true. And it's false only in the case where both P and Q are false. Exclusive or, I'm sorry, I uploaded the wrong slides. So what is the mistake here? Someone?
Actually, we can see only the contents, sir, right now.
You can see only what?
On the first page, I think it shows us contents, a list of contents.
And why nobody's telling me anything? I keep talking. Just wait. Now?
I think it's okay, sir. Logical operators.
Can you see now?
Yeah. It shows the logical operators, right? So.
Can somebody tell me if you can see the slides now?
Yes, sir. Can you hear me? Do you hear me, sir?
I couldn't hear you. Can you repeat?
Do you hear me, sir?
Now, yes. Can you repeat?
Okay. Yeah, I can, sir. It shows us the logical operator exclusive OR, right?
So what is the
Right now,
mistake in this slide?
What is a mistake? Truth table. On a truth table, you mean your?
For example?
Exclusive. Okay, let me check it, sir, please. I think the truth table is wrong. Because the exclusive OR results can be true only both of the inputs should be different.
So yes, the mistake is.
So if P and Q is both are true, the result should be false.
So this one is wrong, right? So
yes, the first line. I mean,
okay.
If P and Q are both true, the result should be false.
Okay, and then we have the conditional statement, which says that if P and Q are propositions, Q if I have too many mistakes. I had fixed this,
I
right?
cannot hear you, sir.
Can you hear me now? Everyone has a problem with
interruption. I mean, your voices are gone frequently.
Can you hear me now?
Right now, it's okay, I think.
Okay, so the conditional statement is true if the. You cannot hear me? Can you hear me? So the conditional statement is true when the hypothesis is true and the conclusion is true, or when the hypothesis is false, and it's only false if the hypothesis is true, but the conclusion is false. Okay? So in every other case, so if what you need to remember is that if, for example, the hypothesis is false, then we don't care about the conclusion. The implication is true. And then we have if and only if, which it becomes false also if the conclusion is false, but true, but if the conclusion is false, but the hypothesis is true. So, and we had how to create new propositions. You have to remember the contrapositive because this is a proof technique, right? Are there questions? I'm going fast through the slides, right? So then when we want to prove something, we can use truth tables. So we have to cover all cases for P and Q. So if P is true and Q is true, if P is true and Q is false, etc. And then we try to construct this expression, this logical proposition, and we build up, right? So we have a NAT Q. So we have a column for NAT Q. Then we have a P or NAT Q, and the truth table is this for that. And we end up with the one, the one we want. So this is a truth table for this expression. I think everybody understands how this is constructed, right? Now, a proposition which is always true, it's called tautology. And a proposition that is always false, it's called a contradiction. So the previous one is neither a tautology nor a contradiction, because sometimes it's false, sometimes it's true. So Baran, P and not P, is a tautology or a contradiction? Elif Nur?
Contradiction, sir.
It is a contradiction. This is always false, right? Bouquet, P or not P, is it a contradiction or a tautology? It is a tautology, you say, because this is always true. Either this will be true or not P will be true. Bartu, is this a contradiction or a tautology? I couldn't hear you. Still couldn't hear you. Emine, Sultan, is this a tautology or a contradiction? It is a tautology. Why? Because why is it a tautology? So it is because if P is true, then this is true, right? If P is because true or something is true. If P is false, then the hypothesis is false. So this is a true statement. So it's true or false, it's true. So it's always true. Enis, what about the next one? So this is a contradiction, because if this is so they have to both be. Can you explain why? So this is false if at least one of these two is false, because we have an end. So if Q is true, sorry, if Q is false, this is true, not Q is true. But in that case, for this to be true, it depends on P. So we don't know. If Q is so that already means it's neither of the two. Okay. So, and then we have logically equivalent propositions, which means just that their equivalence is a tautology. So it's always true. If whatever the truth value of this is the same as the truth value of that. Okay. So these are the Morgan laws, which we saw, and this is how we prove it. So we compare the truth table for this. So this column and that column, and we see it's the same. So this, if and only if this, it's always true because they have exactly the same truth value. Okay. So we'll not do this proof, but then we had this list of equivalences, which you should remember because they're nice. They simplify things easily. Okay. And this was a way to use the simplification rules. So the tautologies. Now we move to the predicate. So this is not really a proposition because it depends on a variable. right? So this is a predicate, P of X. And it assumes a truth value if we assign X a value to X, okay? So these are predicates. So we can have any number of variables. So this is a unary predicate because we have only one variable, or this is a binary predicate, and in general we have an n-ary predicates, okay? And you know this, for example, when you have if statements. Now, when we have predicates, what we do actually usually is a quantification. So the universal quantification of Px is that Px is true for all values x in our domain. And we use this inverted A. So for all x, Px. And we have the existential quantification, which says that there exists one x, at least one x, in the domain such that this is true. And here we use this inverted E. So there exists x such that Px. Is it clear to everyone? You all remember that, right? And in order to prove that such a statement is true, we have to prove it for every x. And it's enough to prove, in order to prove it false, we need just to find one x for which Px is not true. And for the existential quantifier, it's the opposite. So to show it's true, we need to find that one x. But to prove that it's false, we need to show that this is false for every x. So there is no x for which it is true. And this is how we do induction. For example, we have a predicate depending on n, and then we prove that it's true for initial value, usually 1, but not necessarily. And then we show that the conditional statement that says if pk is true, then pk plus 1 is true. This implication, this conditional statement, is true for all positive integers k. So if we prove this, we actually proved Pn, that Pn is true for every integer, non-negative integer, right? And here's the example we used. So we prove that it's true for the basis case when n is 1. And then we assume that pk is true for some k. And we prove that in that case, also pk plus 1 is true. So we proved the implication, the conditional, and then we know that from induction, we know that it's true for all n. Are there questions about logic? No. So what is a set? A set is an unordered collection of objects, okay? And then, I mean, now you should be familiar with this notation, belongs and does not belong, etc. So the elements, so the objects in the set are called elements or members of the set. And we have different ways of describing our set. So we just put it in curly braces, or we can use also ellipses if it is clear what this means. Or we can describe our set with a set builder. We say it's all x's in some set such that some condition holds, some predicate is true, okay? So this is also a very useful notation. So these are all then positive rational numbers, right? So it's all x in the real numbers such that x is a fraction where the numerator and the denominator are natural numbers. So this is a description of the set, but we wouldn't be able to actually write down all the elements. And then we have intervals, and I'm sure you remember how we use parentheses or square brackets to make it closed interval or open interval. Please stop me if you have any question. Now, a set can contain other sets as elements because we just said that the set is a collection of objects and sets themselves are objects. So for example, we can have a set containing these sets, or a set containing this set containing these sets and another set, etc. And when are two sets equal? If they have exactly the same elements. So what does it mean? So A is equal to B if and only if for all x, if x is in A, then x is in B. And this is an if and only if, which means that also if x is in B, then x is in A. Okay? So this is how you prove equality of sets. And we have some special sets. The most special one is the empty set, which is a set containing no elements, and we denote it by this striked 0 set. Okay, it's called the null, empty set or null set. And how do we represent sets? Usually, if they're finite, mostly by Venn diagrams. So we have a circle where we have inside the elements, and the frame outside is the universal set. It's a set of all elements we have in our we consider. Now, a subset is a set containing some of the elements. So A is a subset of B if all elements of A are elements of B. So for all x, if x is in A, then x is in B. Now, which means that this set is inside that set, right? And if we want to prove that something is a subset, we show that if x is in A, then it's also in B. If we want to prove that it's not a subset, then it's enough to find one x such that one x in A such that x is not in B. Okay, and we know that for every set, the empty set is a subset, and the set itself is a subset. A proper subset is a subset that is not the empty or itself. Okay. How do we say that it's a proper subset? This means that it is a subset, and we have the extra condition that there is at least one x that is in B, it's in the larger set, but not in the smaller set. Okay. And if you see this this condition here, it's clear that equality was just a double implication, right? So if we show that A is a subset of B and B is a subset of A, this makes this double implication, which means that they are equal. Now, the cardinality of a set is a number of elements in this set, a number of distinct elements. And if n is a non-negative integer, so this is the cardinality, and we denote it by this vertical, so like the absolute value of A. So this is the cardinality of A is n. If n is an integer, then we say that the set is finite. If a set is not finite, then it's infinite. Now, a special set is the power set of a set, which is the set of all subsets. So we denote it by this calligraphic P of A, and this is a set containing all possible subsets of A. Now, what is the cardinality of P of A? Fatih? Nesdet? Aaron, can you close or answer? Usmane?
It's okay, John.
Sorry?
It is okay.
Yes, but what is the cardinality of the power set of A?
It is the cardinal. It's something like R exponent 2 or R exponent to n.
Well, so if the cardinality of A is n, then what is the cardinality of P of A? Sedef? So Yasin is not n times n.
Yes, sir. And,
Yunus Emre is right. So it's 2 to the n, right? So it is 2 to the n. This you should remember, right? Because let's say we have 3 elements in our set, A, B, C. Now, how do we construct subsets? So we say, first of all, don't take any of these elements, right? Then, which set is this? This is the empty set. Then you say, okay, take only this element. Then you say, take only the second element. Or take only the third element. Or take the first and the second element. Which means that for every element, we have 2 options. So it is 2 to the number of elements in A. Okay? Now, the Cartesian product of 2 sets is the set of all pairs where the first element is from our first set and the second from the second set. Now, what is the number of elements in the Cartesian of product of A and B? Sena. Jakub Han? Exactly. So it's n times m, right? And if we can have the Cartesian product of many sets, and then it's not pairs, but it's n tuples, where the first element is from the first set, the second from the second, etc. Okay? Now we can have set operations of set. So this is the union, for example, of A and B is the set of all elements that belong to either A or B. Okay, so here the Venn diagram is all blue elements are in the union. We have the intersection where it's the set of all elements such that they are in A and in B. So now we have only in this intersection, right? And what do we have more? So what is the cardinality of A union B? So the cardinality of yeah. So the point is, it is not a cardinality of A plus cardinality of B because we overcount some things, right? Some elements were both in A and B, and then we have to subtract them. And this is what we call inclusion exclusion. Do you remember the principle? So the difference between 2 sets A and B, so A minus B, is all the elements that belong in A and do not belong in B. So it's this blue stuff here. You still have no questions. And the complement of a set A are all the elements in our universal set that do not belong in A. And here are some identities, just like we had for logic rules. Okay, so union is commutative, stuff like this. Questions? So now what is a relation? Let's say we have 2 sets A and B. A binary relation from A to B is a subset of the Cartesian product. So it's just a set of ordered pairs, right? Now the first element must be from A and the second from B. And usually we denote it like this, but R has some specific symbol most of the times. But of course, since this is a R, the relation is a subset of the Cartesian product, this is pairs A and B, right? So this was the example. We don't need to go through it again, I think. Let's see this example. Whose turn is it? Serdil Anil, can you tell me which what is the set R? So if A is 1, 2, 3, 4, what are the order? What is the relation where A divides B?
1, 2, sir. 1 and 2.
What do you mean 1 and 2? These are pairs, right?
Yes, sir. Yes.
So how many pairs do we have?
More than one pair,
Sir,
sir.
1 and 1, 1 and 2, 1 and 3, and 1 and 4.
And
Also 2 and 4, sir.
exactly. So this is the divide relation in this set. Okay. Yes, of course I forgot 1 divides 1, 2 divides 2, 3 divides 3, 4 divides 4. Right? Or you forgot it?
Yeah.
Yes,
Say.
sir.
So let's say this can be in the exam question. Now we had properties of relations, right? So relation is reflexive if for all elements in our set, AA is in a relation. So for all A in A, AA is in R. Then R is called reflexive. Now we had some examples. Chatai is R1 reflexive? I cannot hear you really. Yunus Emre?
It is not, sir. Because 3 and 4 not presented in relation.
Okay. But also 2, 2 is not there, right?
Yes.
Okay. And Yasin says that only R5 and R6 are reflexive here, because here we're missing 3, 3, here we're missing 4, 4, here we're missing a lot, but here we have 1, 1, 2, 2, 3, 3, and 4, 4, right? So, is it Chatai? Now, can you answer if divides relation is reflexive? So, Seval? Yes, it is, because every element divides itself. Okay. So now another property is symmetric. A relation is symmetric if BA being in R means that AB is also in R. Okay. So for all A and B, AB is in R implies BA is in R. Seval, which of these relations are symmetric? Omer Farouk? Ahmed Baris?
First one is symmetric. Second one is not symmetric because there isn't a 4, 3. Third one is also not symmetric. Fourth one is also not symmetric. Fifth is not symmetric either because there isn't 4, 2. And sixth one, it's symmetric.
Okay. Do we all agree? Suppose. So is divide symmetric? Baran? No, it's not, right? Because if A divides B, we don't know if B divides A. So it's not symmetric. Now, be careful, antisymmetric does not mean that it is not symmetric. Okay, antisymmetric means something different. It means that if A and B is in R and B and A is in R, then A is equal to B. So for all A and B, if these two conditions hold, then A is equal to B. Bar 2, which ones are antisymmetric?
Oh.
Is the first one antisymmetric?
No.
No, right? Because you have 1, 2 and 2, 1, but 2 is not equal to 1.
Yes. The second is antisymmetric. Is it? Yep. Yes. Is it?
I don't think so, because 1, 2 and 2, 1 is there, but 1 is not equal to 2.
Oh.
So Sena gives you some hint. If there is one symmetric pair, then it's not antisymmetric. Right?
Yes.
And Omer Farouk says, so R3 is
Antisymmetric.
it is antisymmetric, R4 and R5. R5, I'm not 100% sure. Yeah, maybe. Yes. Okay. Is divides relation antisymmetric? Bouquet.
Yes, it is antisymmetric.
Why?
Because there is not going to be a symmetric pair.
Wait, but that's not a definition. So the fact that there is no symmetric pair does not mean that. So what we need to prove is that if A and B is in R, if A divides B and B divides A, then A has to be equal to B.
Yes.
The fact that it's not symmetric is not enough.
Yes.
A relation may be neither symmetric nor antisymmetric. So divides is antisymmetric because if A divides B and B divides A, then we can prove that A is equal to B. Okay?
Okay.
Transitive. So if we have A and B in R and BC in R, then AC is in R. So for all A, B, and C, if these two holds, then AC is also in R. Elif Nur, which of these are transitive?
Sir, R1 is transitive. Just
Okay.
a second. Okay. R2 is not.
Why?
Why? Because of R2s include 3, 4, but 3, 4, 4, 1, but it's not include 3, 1.
Exactly. So good. Thank you. So we see how we prove that something is not transitive, right?
Yes.
Okay. Is divide, so Emine Sultan, is divide transitive? You think? That's not a valid answer. I mean, I'm asking you what you think anyway, but is it yes or no? So why do you think it is transitive? So the point is, yeah, so So if we have, so for these things, usually we do it, we prove it like that, right? So we say that, so A divides B. What does it mean? It means that B is K times A, right? And B divides C, it means that C is L times B. Now from here, what we can say is that C is L times K times A, right? And this is also an integer, which means that A divides C. And this is why it is transitive. Yeah, okay, we can combine relations, that's fine, because they are just sets, right? Sets of pairs. And we can do whatever we do with sets. And we can have n-ary relations. Now, we have two main types of relations. One is equivalence relations, which are relations that are reflexive, symmetric, and transitive. And then if two elements are related by an equivalence relation, we usually write this triple equal. Okay, we say A is equivalent to B if they're related by an equivalence relation. For example, this should be A minus, sorry, we have the relation that A and B is in R if and only if A minus B is an integer, where A's and B's are real numbers. So this is an equivalence relation because it is reflexive. A minus A is 0, which is an integer. A minus B is an integer. If A minus B is an integer, then also B minus A is an integer. It's just the negative, the same result with a minus. And if A minus B is an integer and B minus C is an integer, then also A minus C is an integer. So this is an equivalence relation. Okay. Now, if we have an equivalence relation on a set A, then the set of all elements that are related to an element A through this relation, this is the equivalence class of A. Okay, and we denote it by something that is not visible here, right? Ah, no, it is by this A of R. So R is the relation, right? So what is an equivalence class? So if we have an equivalence relation, then the following are equivalent. So A and B are in R. The equivalence class of A is the same as the equivalence class of B because they are sets, right? And they're equal as sets. And the intersection of the two classes is not empty. If it is not empty, then they're equal. This, for example, I may ask you to prove in the exam that if you have two equivalence classes and the intersection is not empty, prove that they're equal. So, questions about equivalence classes? Okay. Let's go for the other big family of relations, which is order relations. A relation is called an order relation, a partial order, if it is reflexive, antisymmetric, and transitive. Okay, and a set together with a partial ordering, it's called a partially ordered set or poset, and we denote it like this. So we have our set and the relation on A. So Z together with a smaller equal is a poset, right? Because this is an order relation. If we take two integers, then it is reflexive because every integer is smaller or equal to itself. It is antisymmetric because if A is smaller or equal than B and B is smaller or equal than A, then A is equal to B. And it is transitive because if A is smaller or equal to B and B is smaller or equal to C, then also A is smaller or equal to C. So, for example, also the power set together with inclusion is a poset. That's another possible question. Now, two elements of A and B are called comparable if either A is related to B or B is related to A. If they're not comparable, they are called incomparable. Okay. For example, in this poset, are 3 and 9 comparable? Enis. Elifnur.
Yes, sir.
They are. And how do they compare?
I didn't explain, but I think in other slides page, we said that if poset z and greater than equal, less than equal. I didn't explain, sir. I'm sorry.
No, but let's think about it. So, is 3 and 9 related?
Yes.
Yes, because 3 is smaller than 9, right?
Yes.
That's it. Okay, is 3 and 5 comparable in the poset of non-negative integers of positive integers with division? Jakub Han. They're not comparable. Neither 3 divides 5 nor 5 divides 3, right? So they're not comparable.
So it cannot be a relation also, right? So
why?
Cannot be a poset, an element of poset, because 3 cannot be divided by 5, or 5 cannot be divided by 3.
Yes,
so
but
it's
that's
violist rule, I think.
What rule? We don't have any rule saying that all elements must be comparable.
No, rule. I mean the operations. I mean division operations. So the result cannot be a positive integer. So it cannot be an element of poset.
Yeah, but why? I don't see why it cannot be an element. The fact that two elements are not related doesn't mean that in general they're not in the poset, right? If you have, I mean, not everything has to be comparable.
So it can be in a poset, but cannot be comparable also.
Yes,
But
this is why we actually have this. We have the definition, right? Otherwise, we wouldn't even talk about incomparable elements. So it's possible to have elements that are not comparable. And we will see this example, right? I mean, we have seen this example many times. So in the 1, 2, 3, 4, right, together with divisibility, what was this poset? The Hasse diagram, which we will see soon, was 1, 2, 3, 4. 4, right?
Yeah.
Is 3 and 4 comparable?
Can be separated.
No. Forget about 5. 3 and 4, are they comparable?
No, can. All right.
They're not.
No, they are not.
So, but they're definitely elements of this poset, right?
Yeah. I can see so. Okay, it's okay. Thank you.
So, Sena, yes, if it was the real numbers, then everything divides everything. I agree. They would be comparable. And how do I? Now, a total order is when we do not have incomparable elements. So, for example, in the divisibility, we saw before that there are incomparable elements, so it's not a total order. But if it is a total order, then if everything is comparable, all pairs of elements are comparable, then we call it a total order. For example, Sena's example, with real numbers, this would be a totally ordered set. Yes. Here's the non-example and the example, right? So every integer is either greater smaller, greater, equal, or not by any other. Here we can compare everything, but here we cannot. And the set is called well-ordered if it is a poset that has a total order and every non-empty subset has a least element, has the smallest element. Okay, so here I should have a second Z. For example, this set is not well ordered because if we take a subset, it's not necessary that it has a least element, right? Minus infinity may be there, and minus infinity of then we cannot take the smallest element. Okay. And the Hasse diagram is if we take the directed graph for the relation, then we remove loops and transitivity condition, right? So we take this and we remove the things that we don't need that are implied by the rules of a order relation, right? And then we have this is the Hasse diagram. So this is another Hasse diagram. We start with this and we remove the unneeded stuff. By the way, this is a theory. When you draw a Hasse diagram, you never start from here. You just don't draw the things that you don't need, right? You immediately draw this one. But for example, you say again 8 and 12 or 8 and 6 are incomparable elements. Now, what is a maximal element? A maximal element A in our set is so I said an element A in A is maximal if, so we have a poset, right? If there does not exist another element that is greater than that. By the way, greater, I use this, but it could be any relation, any order relation, right? Now a minimal is if there is no B smaller than A. This is maximal and minimal. Now greatest is if A is bigger than any other B, and least if A is smaller than any other B. Okay. Be careful, greatest and maximal, they're not the same. Okay. For example, is 20 maximal? Bouquet?
Yes.
Is it greatest?
No.
Why?
Because it doesn't have connection with all elements.
So what you say is that 20 is not larger than 12, right? So there is a B, 12, for which 20 is not greater than 12. I agree. So because there is no connection, this is what you mean, right?
Yes.
Good. So now, if we take a subset of our set, where our set is a poset, right? Then we have the upper bound, which is an element U such that every element in B is smaller than U, smaller or equal than U. And the lower bound for B is an element of A such that all elements of B are greater or equal than L. Okay? So, and we may have many upper bounds and lower bounds, right? And then special ones are the least upper bound, which is among all the upper bounds for B, the least one, the least element, and the greatest lower bound, which is among all the lower bounds, the greatest one. Okay. So if I take as subset if I take this as B, bar 2, what is the least upper bound? Baran. E and F. So E and F indeed are upper bounds. And what is the least upper bound? E, right? Because E is smaller than F. To go to Sena's question, so A is the greatest element if for all other elements B is smaller than A. So yes, it has to be comparable with everything else, right? Okay. And now, when do we have a lattice? A partially ordered set in which every pair of elements has both an upper and so a great greatest, so a least upper bound and a greatest lower bound, then it's called a lattice. So, for example, the first one, is it a lattice? Or the second one, is it a lattice?
Sir, could you give example about lattice? Because I don't understand definition.
So here, if we take any pair, let's take C and D, okay? So they have their least upper bound is E and their greatest lower bound is B, right? Now, if we take, let's say C, I don't know, and B, then their greatest lower bound is B and the least upper bound is C. Every pair has this property. What about the third one? Are they all lattices? No. So if we take these two elements, then they have two upper bounds, right? And there is no greatest, there is no lowest least upper bound because we cannot compare these two. So this is not a lattice. Right? There's no unique. This is a lattice because if we take any two elements, well, we will end up either with this one. I don't know. This is also not a lattice. Because if I take these two elements, no, this is a lattice because if the least upper bound is this and the greatest lower bound is that. Okay. So, and then we have functions. Other questions for until here? No. So for functions, a function is an assignment of elements from A to elements of B. I will not spend too much time for this because you have seen it many times, right? So A is called the domain, B is called the codomain. If we have an element of the domain and
f of a is the image and a is the pre-image, right? And the range or image of a function is the set of all images in the codomain, which is not necessarily all of the codomain. Now, well, okay, you can play this game anytime in your own time, but remember we can add and multiply. But more importantly, we have three properties for two properties for functions. So a function is called one-to-one if we have that whenever the images are the same, then the pre-images are the same. Okay, then it's a one-to-one function. This means that we cannot have two elements go to the same in the other side. Now, onto or surjective, it means that for every element in B in the codomain, there exists an element of the domain such that the element of the codomain is the image. So this means that every element in B in the codomain has a pre-image. So the image of our function is the whole codomain, like here. And if we have a one-to-one and onto, then we call it a bijection. So this means that so which one of these are bijections? Eren. Emirhan. Fatih.
So the third one and the last one, I think.
The third and the last, sorry, are so this is a bijection. So yes, it is one-to-one and onto. This is not onto because you have an element that is not covered. This is also not onto. And is the last one one-to-one and onto? So it's not one-to-one, right? Because A, this is not a function.
I didn't see that, sorry.
This is not, the last one is not a function, so it's definitely not a bijection. Okay. If we have a bijection, so if we have a one-to-one function, then we actually have also the inverse, which just takes elements from the other side and brings them to their pre-image, right? We go back. And if we compose f with f inverse, then we get the identity. So are there questions about the algebraic structures we said? So we have associative, commutative, and distributive properties, and we had some special elements like the neutral element and the inverse element. The inverse element is if we have an operation A and B, then it gives us the neutral element. Then B is the inverse of A, right? So I don't want to spend too much time, but I just want to remind you that we had this group-like structures, which is semi-group, monoid, and group. And we had some nice examples, right? And then we have ring-like structures. I will update my slides. I'm very sorry. I mean, it's not serious mistakes, but maybe misleading. So ring-like structures. And then we saw how we define operations on sequences. And we saw that convolution and addition. And we saw this is the power series, the set of formal power series. Okay. And then we saw that the set of finite power series is the set of polynomials, the ring of polynomials. Do you remember this? Now, the whole point of doing this algebraic stack was to see that we can construct complicated objects like polynomials, but they behave like integers. If we have a ring, then they have the same kind of properties. They implement the same interface in Java terms. So, and then if we have a ring, we can take the field of fractions. In a ring, we cannot divide, but let's say we want to divide. So if we have integers, what we do is we take rational numbers where we can divide. So the field of fractions of integers is the rational numbers. And the field of fractions of polynomials is rational functions, which are just fractions of polynomials. Okay? So as I said, I don't want to go into these details, but if you have questions, you can ask me. And so today is the last lecture, right? So there will be an exam on 22, I believe. It will be announced. Is the schedule announced already?
No, I think so, not yet.
Okay. So I think it will be on 22 or 21. I don't remember. So a Friday. So questions? You have no questions. That's great.
Sir, I have a question. Can you hear me, sir?
Sorry. Yes, I can hear you.
I don't understand lattice part in third diagram.
Okay.
Please, could you open?
Can you see now?
Yes, sir.
So, what is an upper bound? So it has to be the least element among upper bounds. Okay. So here, what happened is that actually we have so if we take this element and that element, right? So what are the upper bounds of these two elements? It is this, that, and that. These are all upper bounds for both B and C, right? For B and C. Do we agree?
Yes, sir.
And now I want to take the list of these elements. Which one is it?
We can't, sir.
There is no list upper bound, right?
Yes, yes.
So it is not a lattice because every pair has both a list upper bound. Well, this doesn't. I found a pair that does not have a list upper bound. But here, it is not the same because if I take, for example, these two things, what are their upper bounds? It's only this.
Why we don't include E and G?
Sorry, E and G. This is not because E is not greater than D. E is not a bound for both B and D. It's only for B.
Okay, sir. I got it. Okay.
Okay.
Thank you.
You're welcome. More questions?
So, can you give any information about the weight factors of the lectures? I mean, for example, maybe recurrencies has a much more weighter than the other lecture, something like this.
No, even if I could, I wouldn't.
No.
So,
all right.
So I can tell you that recurrences definitely will be there.
Definitely. Okay. All right, sir.
Yeah.
Thank you.
More questions?
Do we responsible for the Turing machine too?
So probably Turing machines will not be in the exam. Yeah.
Okay, thank you.
So I don't know how you like the topics we discussed in this lecture, but and obviously you don't know, or you haven't seen my research most probably, but some of you may be interested in having small research projects, and we can discuss about this. So I will send a link. I put another meeting ID. Do you see in the chat? So if you're interested in some research project, by the way, this has nothing to do with your discrete math lecture anymore, okay? This will not play a role, neither positive nor negative or anything. Just if you're interested in a research project in topics related to discrete mathematics, in the sense, so we'll do algorithmic mathematics mostly. So we develop the algorithms and we use some of the tools that we discussed in this course, and mostly implement these things. So in new languages, in computational platforms, let's say. So if you're interested, join now. We can talk for 10-15 minutes in the link I sent in the chat. Do you see the link? I hope so. So if you join the meeting, doesn't mean that you have to do, but if you may be interested, let's talk a bit, okay? Otherwise, good luck with your exams. Yes?
Please, I have a question also.
Yes?
My first quiz, I missed it because of connection. I did the second one. I don't know if I can have another chance to get the last one that I
so this you will have to discuss with Gizem. So I don't know what will happen with, we will see in general how many problems we have with connections, what happened in general, and we will definitely be, we'll try to help, because this semester is not a normal semester, but also we have to follow some rules, okay? Also about the exam, since the whole department decided to have a uniform way of doing exams, we will also follow that. I prefer different ways of exam, but I will follow the style of the department, okay?
Thank you.
Okay. Then good luck with your exams, and see you in the other room if you're interested, just to discuss a bit. Bye.
Thank you very much, sir. Bye.